Hi, this is Fazil Kar from Faculty of Engineering Sciences. Today I'll be conducting a tutorial on Chapter 2 and 3. I'll be solving some problems from Fall 2021 mid and final examinations. As you can see that we have a function for which we have to find whether the function is continuous, for which interval the function is continuous. So we have to find the intervals where f of x equals to 1 over x minus under root of x plus 6 over x squared plus 1 plus modulus of x squared plus 1 plus sine x. One way of approaching this problem is that we can split this function into 4 different parts, 1 over x, and this under root part, this modulus part, and this sine x part. And we can check for each of these 4 different parts for which the points at which the function is discontinuous. So if we take I of x equals to 1 over x, we know that function is not defined at x equals to 0. So this gives us the domain of this function equals to minus infinity to 0 union 0 to infinity. We'll do the same thing for the second function. We'll take it as capital F of x equals to under root of x plus 6 divided by x squared plus 1. So as we know that the denominator will always stay positive and greater than 0, so the denominator will always stay defined for all real values of x. But in the numerator, we know that x plus 6 should never be less than equal to 0, so it should always be greater than equal to 0. So this gives us x is greater than equal to minus 6, and this way the domain will come out to be minus 6 to infinity with minus the closed interval on minus 6. We'll do the same for mod x. So we'll take it as g of x. G of x equals to modulus of x squared plus 1. So we know that for all real values of x, and this function is defined, so domain comes out to be all real numbers. So we'll do the same for k of x, which is equals to sine x. And we know that the domain of sine x is actually all real numbers. Now, out of all these 4 functions, this function number 1, the domain of function number 1, function number 2, number 3, and 4. What we'll do is that we'll find the common domain at which lies in all of these 4 functions. So that common domain comes out to be minus 6, this, 2, 0, because 0 is not included in 1 by x, union 0 to infinity. So this is the common domain for which this entire function, the combination of these 4 functions, will be continuous on this interval. We'll move on to the next question, question number 2. So the question number 2 is we've been given a piecewise defined function, and we have to find the values of a and b for which this function is continuous for all real numbers. So one way of approaching that is that we have to make sure that at the endpoints of the interval, this 0, 0 and 1, 1, the left-hand limit and the right-hand limit should be equal to each other. So we'll start by checking the left and right-hand limits for when x is at the endpoint x equals to 0. So to do that, we have to make sure that x approaches to 0 negative, g of x is equal to limit x approaches to 0 positive, g of x. So this gives us limit x approaches to 0 negative, 1 plus a plus b e raised to power x equals to limit x approaches to 0 positive, ax squared plus bx plus 3b. So we'll have to make sure that for 0 plus, we're using the second function because 0 plus lies in the second interval. And for 0 negative, we have to use the first function because of 0 negative lies in the domain of the first interval. So this will give us 1 plus a plus, so e power 0 equals to 1. So this will give us b dot 1 equals to, this will come out to be 0, this will come out to be 0, and we'll be left with 3b. So in the end, we'll be left with a minus 2b equals to minus 1. So that will be our first equation. Moving on to the second endpoint, which is x equals to 1. So for the second endpoints, we'll have to do the same thing, limit x approaches to the left-hand limit of the function and the right-hand limit of the function. So for the left-hand limit, we have to use the second function, and for the right-hand limit, we have to use the third function. So this will give us ax squared plus bx plus 3b limit x approaches to 1 negative and limit x approaches to 1 positive. The third function is a cos of pi x plus bx. So if we put in the limits, we'll be left with a plus b plus 3b equals to, so we know that cos n pi equals to minus 1. So cos 1 pi will be equal to minus 1. So we'll be left with minus a plus b into 1. So if we solve this, this b will cancel out with this b, and we'll be left with 2a equals to minus 3b. And from here, we can say a equals to minus 3b by 2. If we put this function, this value into the first equation, so this is our first equation, this is our second equation. So if we put this value into the first equation, this will come out to be minus 3b by 2 minus 2b equals to minus 1. So minus 7b divided by 2 equals to minus 1, and b will come out to be 2 by 7. If b is 2 by 7, then a will be minus 3 by 2 into 2 by 7. So this will give us a equals to minus 3 by 7. So a equals to minus 3 by 7 and b equals to 2 by 7. That will be our answer. So moving on to the next question. This is actually question number 3 from the Fall 21 final examination. So the question says, find the values of a such that the line y equals to x plus 3 is an oblique asymptote of f of x equals to x squared plus ax plus 3. So as we know, we can see from this function that the degree of the numerator is 1 greater than the denominator. So we can say that this function is actually has an oblique asymptote. So in order to find it, what we'll do is we'll just simply apply long division. So for long division, what we have to do is that we have to divide this function x squared plus ax plus 5 by x plus 1. So in order to cancel out this x squared plus x squared, we'll multiply it with x. This will give us x squared plus x. If we subtract this, we'll be left with, this will cancel out, and we'll be left with a minus 1 into x plus 5. So multiplying x plus 1 with alpha minus 1 or a minus 1, we'll be left with a minus 1 into x plus alpha minus 1. And this will give us, if we minus this, we plus this, and we minus this, we'll be just left with 6 minus a. So in the end, the quotient comes out to be x plus a minus 1. So x plus a minus 1 should actually be equals to x plus 3 because the oblique asymptote is actually the quotient in the long division. So in this, the x's will cancel out and a will come out to be 4. So that's our answer. If you need to verify this, what you can do is you can substitute back this a value back into the function. So f of x becomes x squared plus 4x plus 5 over x plus 1. So if you apply long division on this, what you'll be left with is multiplying x plus 1 with x. This will give us x squared plus x. You'll be left with 3x plus 5. You multiply this with 3, you'll be left with 3x plus 3, and you'll be left with 2. So this quotient is actually what we needed, and this is coming out to be exactly y equals to x plus 3. So your equation will become y equals to x plus 3 plus 2 over x plus 1. So this is actually our leading value, and this is our lagging value. So the leading value is actually the asymptote. So this y equals to x plus 3 becomes your asymptote. Moving on to the next question. We have question number 4. That is same from final examination fall 2021. So the question says, for what values of a, b, and c, the tangent line to the curve y equals to ax minus x squared is also tangent to the curve y equals to x squared plus bx plus c at the point 1, 0. So we've got two curves. We have to find for which values of a, b, and c the curve has the same tangent at the point 1, 0. So starting off, first of all, we have to see this equation in order to find any unknown values. So is there any way we can just put in some of the given information and find our unknowns? So if you notice that in the first curve is passing through the point 1, 0. So if we plug in 1, 0 into the first equation, we'll be left with y equals to ax minus x squared. Y of, so the y is 0 over here and x is 1. So y of 1 equals to a into 1 minus 1 square. So y of 1 is actually 0. So 0 equals to a minus 1. So over here, alpha or a comes out to be 1. Moving on, we know we have to find the tangent to the first curve. So if we find y dash will come out to be a minus 2x. So a, we know that a is actually 1. So it comes out to be 1 minus 2x. So this is y dash. So we know that the tangent is passing through the point 1, 0. So at point 1, 0, the value of x is 1. So y dash of 1 is equal to 1 minus 2 into 1. So this comes out to be minus 1. So this is actually the slope. This is actually y dash. So this is actually the slope of the curve at the point 1, 0. So we'll use this y dash value in the second function. So as we know that the second function is also passing through point 1, 0. What we'll do is the second function gives us y equals to x squared plus bx plus c. Okay, so what we'll do is that we'll simply take the derivative of the second function. This will come out to be y dash equals to 2x plus b. So we know that the tangent for what values of a, b, c, the tangent line to the curve is also a tangent to the curve, to the second curve at point 1, 0. So if it is also tangent to the curve at the same point, we have to we know that the tangent lines have two similar tangent lines have same slope. So the y dash that we found out for the first function, it would be the same for the second function. So we'll simply plug in -1 equals to, so y dash equals to -1 and 2x plus b. So this is tangent at the point 1, 0. So this comes out to be -1 into equals to 2 into 1 plus b, and b comes out to be -1 minus 2, and from here the b is -3. So b is -3 and a is 1. We are left with c. So how we can find c is, we can just plug in the values of y equals to x squared plus bx plus c. So we know that the point is 1, 0. At 1, 0, 0 equals to x squared becomes 1 plus b into 1 plus c. So c comes out to be minus b minus 1. So we know b is -3. So -3 minus -3 becomes +3 minus 1. 3 minus 1 equals to 2. So in the end, we have a equals to 1, b equals to -3, and c equals to 2. Thank you very much. So we'll start by solving the first function. So we have y equals to ln of under root of sine theta cos theta divided by 1 plus 2 ln theta. So what we'll use over here is the property of ln a over b, which is equal to ln a minus ln b. So this comes out to be y equals to ln of sine theta cos theta raised to power 1 by 2 minus ln of 1 plus 2 ln theta. So as you know that ln of a power b is actually equals to b dot ln of a. So we'll be using this property in the first term, and this property we've used already, and this we can just directly derive. So start using this property over here. This comes out to be y equals to 1 by 2 dot ln of a dot b. So as you know, ln of a dot b is equal to ln of a plus ln of b. So this will become 1 by 2 ln of sine theta plus ln of cos theta. And this will become minus, this will stay the same, minus 1 by minus ln 1 plus 2 ln of theta. So now we can easily differentiate this function. So starting from the first term, we can just write y dash equals to 1 by 2 into, so ln sine theta derivative is actually 1 over sine theta into the derivative of sine theta, which is cos theta, plus ln of cos theta. So what this becomes 1 over cos theta dot derivative of cos theta. That becomes minus sine theta. And then we have minus the derivative of 1 plus 2 ln theta is actually 1 over 1 plus 2 ln theta dot the derivative of the internal function, and that is 2 by theta. So if we write it all together, this becomes 1 by 2 cos theta plus sine theta is actually cotangent theta, and minus sine theta by cos theta is actually equals to minus tangent theta, minus 2 by theta into 1 plus 2 ln theta. So this will be your final answer. Now moving on to the next part, this seems like a similar question. So we'll try to solve this one. Y equals to under root of x plus 1 raised to power 5 divided by x plus 2 raised to power 20. So this is actually the under root comes for the whole numerator and denominator. So how we'll start this problem is, this is a similar problem. We'll use the same properties. So for y equals, so there is an ln2, I guess. Yes, there is an ln2, so we'll just put an ln before that. So we'll use the same properties, ln of, so this is actually a power b over a2 power b2. A1 power b1 and a2 power b2. So a1 power b1 is actually ln of x plus 1 raised to power 5 by 2, and a2 power b2 is actually x plus 2 power 20 by 2, which is 10. So this comes out to be, if we simplify this function, this comes out to be 5 by 2 ln of x plus 1 minus 10 ln x plus 2. So this will become 5 by whole divided by 2 into x plus 1 into x plus 2, and this 5 will become 5 dot x plus 2 minus, so this 2 will multiply with 10 and this becomes 20 into x plus 1. So the final answer you'll be having is 5x plus 10 minus 20x minus 20 whole divided by 2 into x plus 1 into x plus 2, and this becomes minus 15x minus 10 over 2 into x plus 1 into x plus 2. So that would be your final answer. Thank you very much. Question that wants us to find the limit of this function when x approaches to 1. So how about now the problem in this function is that normally in a function that has an under root, we rationalize the function. But rationalize the function in such a way, in this case, wouldn't do any benefit. So we can transform the function maybe like this: limit x approaches to 1, cube root of x minus 1 divided by under root of x minus 1. Now you have to look at the highest power of the root in the entire function. So over here you can see this x has the power of 1 by 2 and this x has the power of 1 by 3. 1 by 2 is actually greater than 1 by 3. So what we can do over here is we can actually take the difference of the two powers, and this will give us 1 by 6. So this actually means that x raised to power 1 by 2 can be written as the product of x raised to power 1 by 6 and x raised to power 1 by 3. What is x raised to power 1 by 6? This is actually the under root of x raised to power 1 by 3, and this is x raised to power 1 by 3. So what does the function transform into? So we have limit x approaches to 1, cube root of x minus 1 divided by under root of x raised to power 1 by 3 dot x raised to power 1 by 3 minus 1. Now over here, you can see that we still cannot rationalize this function. It wouldn't do us any benefit. So what we can do is that we can make a little bit of limit substitution. So let's say k equals to under root of So let's just say y equals to under root of x raised to 1 by 3. Now the limit of x is actually x approaches to 1. So if x is approaching to 1, what is y approaching to? So when x approaches to 1, y is approaching to 1, right? Now what we have to do is we can transform the limit to limit y approaches to 1. So the cube root of x is actually y minus 1 over cube root of x whole square root. This becomes under root y, and x raised to 1 by 3 becomes y minus 1. So this will turn into y minus 1 over under root y dot y minus 1. Now we can do another limit substitution. We can say k equals to under root y. Now y is approaching to 1. So when y approaches to 1, we can say that k approaches to 1, because when we put under root y equals to under root 1, this gives us 1. So if we have to proceed further from here, we can have another function limit k approaches to 1. So k is actually under root y. So y becomes k square minus 1 divided by under root y becomes k dot y becomes k square minus 1. So this becomes limit k approaches to 1. So k square minus 1 is actually k plus 1 into k minus 1 whole divided by k cube minus 1. Now we know that k cube minus 1 is actually a cube minus b cube. So what is a cube minus b cube? So a cube minus b cube is equal to a minus 1 into a square plus b square plus ab. So in this case, it's k cube minus 1. So this becomes k minus 1 into k square plus 1 plus k. So if we replace this over here, this becomes limit k approaches to 1, k plus 1 into k minus 1 whole divided by k minus 1 into k square plus 1 plus k. Now you can see that k minus 1 cancels out with k minus 1. So we're left with limit k approaches to 1, k plus 1 whole divided by k square plus 1 plus k. So this turns out to be 2 divided by 1 plus 1 plus 1, 3, and that is your answer. A function y equals to 4 sine under root of 1 plus under root of t. We have to find the derivative of this function. So in such a case, we normally apply chain rule. How can we start? There's a direct method to solve this question, and there's a proper chain rule method to solve this question. So let's say that the function is 4 sine under root of 1 plus under root t. So in this, let's say we say u equals to under root of, so u equals to 1 plus under root of t. And let's say that v equals to under root of u. So what I have done over here is that the inside term in the under root, I've taken it as u, and the outside term, which was under the outside square root, I've taken it as v. So v equals to under root u, and the u contains 1 plus under root t. So what does y become? Y becomes 4 sine v. Now what we have to find over here is that we are actually interested in finding dv and dy by dt. But now we have the function in y and v. So here we would have to apply the chain rule. So y is actually a function of v is actually a function of u, and u is actually a function of p. So how do we apply the chain rule over here? Now we have to find dy by dt. So how would we go about this is, in order to find dy by dt, you would have to pass through v, u, and then you have to go towards t. So dy by dt is actually dy by dv dot dv by du dot du by dt. As you can see, dv cancels out with dv, du cancels out with du, and we are in the end left with dy by dt, which is equal to the left hand side. So the right hand side and the left hand side should always be equal to each other after canceling out terms. So what is actually dv by dv? So dv y by dv is actually 4 cos v. So we'll just put in the term over here, 4 cos v. What is dv by du? dv by du is actually 1 by 2 under root of u. And what is du by dt? Du by dt is simply the derivative of 1 is 0, and derivative of under root t is 1 by 2 under root of t. Now, if we plug in the terms back into the v and u, what does it become? So the 2 cancels out with 4. So we're left with cos of v dot 1 over under root u dot 1 over under root t. So what is cos v? Cos v is actually cos of under root u, and cos of under root u is under root of 1 plus under root t. So cos v becomes cos of under root of 1 plus under root t dot, what is 1 by under root u? 1 by under root u is actually 1 divided by 1 plus under root t, and this is being multiplied with 1 by under root t. So this is actually dy by dt. Now this was the long method. What if we have to directly apply the chain rule, but just looking at a function? So the direct approach is actually pretty simple. What we do is that we start with the outside function and we keep on going inside. So for example, I have to find dy by dt. So this would be actually the derivative of the outmost function. So the outmost function is 4 sine, and then there is some term inside. So this becomes 4 cos of under root 1 plus under root t. And then I have to move into the inner term. The inner term is actually the outer bracket. So what is the derivative of the outer bracket? So the derivative of the outer bracket is 1 by 2 under root of 1 plus under root t. Now, after calculating the derivative of the outer bracket, you have to slip in one more bracket. So after going inside, I have to also find the derivative of 1 plus under root t. So that turns out to be 1 by 2 under root t. The 2 cancels out with 4, and we're left with cos of 1 plus under root t whole under root dot 1 plus under root of 1 plus under root t dot 1 divided by under root t. Now, if you compare this function with this function, these two functions are similar. 1 by under root t, 1 by under root t, 1 by under root of 1 plus under root t, 1 by under root of 1 plus under root t, cos of 1 plus under root t whole under root, cos of 1 plus under root t whole under root. So this direct method generates the same result as this method. So over here, even we are doing actually applying the chain rule, but this is actually a more neat approach, which describes a step-by-step approach of how to apply the chain rule. Thank you.